So we did prove this, that if you have f is continuous from 0, 1 to r, right? So this implied that f is uniformly continuous. Yeah, and Raghav also had some timing issue. He wanted me to do on Saturday evening, but Saturday evening is not possible for me, and Sunday evening is also not. So, yeah. Anyways, we proved that f is uniformly continuous. Right? The uniformly continuous would basically mean that it doesn't depend on the delta. Right? So this is just that given for all epsilon, not for all epsilon, given epsilon, so epsilon greater than 0 uh, implies that there exists a delta that fx minus fy is less than epsilon if x minus phi is less than. So this we have proved. Right. So how can we use this? How should we use this? Let us try to so there is one thing in uniform continuity which is maybe okay, before that let's come to this thing. How did we prove it, right? So we basically at every point, so we had this interval 0, 1, right? We had the interval 0, 1, and how did we prove it? So like for each point x naught, we found the delta for every point, right? So that whenever you pick 2 points in this, then they are epsilon close. And then our assumption, and this I think is maybe what we should prove, right? Yeah, our assumption was that there are finitely many intervals do it, right? And that sort of we understood boils down to saying, or I mean, it's clearly enough to prove that given any cover of 0, 1 using these intervals, there are finitely many intervals that will do the same cover from that cover. Okay, so given any cover of 0, 1, there is a sub cover of that which is finite and yet it covers, and it comes down to this. Obviously, that's enough to prove this, but also we notice that you can have all kinds of functions and all kinds of intervals, and for each time you're getting finitely many. It has something to do with the interval itself. So assumption was that given so notation has to be written in a certain way. Let us say that you have some intervals, and let's say these are open intervals, okay? Or maybe back to no. AI, BI, and this union of AI, BI is covering 0, 1, right? The thing that was remaining was, if we want to prove that this implies that there is finitely many among these which cover. So there exists finitely many. It could be any number, arbitrarily large, but it's finite. But these also cover 0, 1. Right? So can you say from this, assuming this assumption, how did we finish the proof? So like, if once you have this, then what happens, right? Once you have this, then you have finitely many intervals. Now, our goal was the following, right? Our goal was that when you pick 2 points, it should land in one of those intervals. Otherwise, you cannot guarantee that f of x minus f of y is less than epsilon, right? So the goal was that you pick 2 points, it should be one of those intervals. So how do you guarantee that? Well, you guarantee that by picking, so now your delta should be the minimum of the intersections, right? Of these like overlaps. If it's minimum of the overlaps, maybe a little less than the minimum of the overlaps, then then when you pick 2 points with that distance, right? So this implies that x minus y less than delta would imply that x and y belong to some interval. Among those finitely many. And then we are done. So there are 2 aspects to this. One is that this fact needs a proof, right? But the second is that what we did here, how can we see that in 2 dimensions? How can we do that in 2 dimensions? So let us just try to imagine it for a little second, okay? Because so usually this proof, uniform continuity proof, and here we've not the uniform continuity proof totally, but this fact that you have these finitely many covers, finitely many intervals covering. So I'm not talking about this assumption, but this existence of such a delta, this thing. That assumption, obviously, that is a property called compactness. But this delta is usually portrayed as, usually taken as another property, which is a big theorem. What is that? So this is here, we find a delta such that you pick any 2 points and it is in one of...
Theorem.
Sorry?
It's called Heine Borel theorem, right? You have got
Heine Borel. So this could be called Heine Borel theorem,
right?
Okay. Yeah. So, but yeah, this is there. This is a separate thing. This we will come to. But on top of that, there is another thing which, because this was not enough, right? We needed this also. I mean, not this. I mean, we needed this existence of this delta, or
Existence
rather,
of the smallest delta.
Yes, right. And in one dimension case, as you can see that probably that's what you were saying, that it's basically Heine Borel. In one dimension case, existence of that delta is quite easy, right? We did it last time. Maybe it's not trivial, whatever, but it's not difficult. Right? You just take the minimum of those intersections, and that delta works. But it's a pretty interesting delta, because you pick any 2 points, it is in one of them. Right. It's an interesting thing. Right? My point is, how do we see this in 2 dimensions? Okay. Before that, but why I repeated this thing is that, so usually when people prove this, they don't see the existence of this delta via this combinatorial way. Okay. This existence of this delta is proved in arbitrary metric space. Okay. And then it is said, okay, then it will hold everywhere. But the good thing is that in one dimension, the existence of this delta is just a simple thing that one can see.
Set theory argument.
Yeah, just basic. But the good thing it is true in general. So let us just take
how do we prove it in arbitrary metric space X? Like,
yes, in arbitrary metric space X, the proof is there. It is not difficult, and it is called the Lebesgue number lemma. This delta is called the Lebesgue number, but it's not, whether it's difficult or not depends on how well you understand, how do you understand the things before it, right? But it is called the Lebesgue number lemma. How it is proved, we can come to that, but maybe not today. That's the theorem that comes later. But let me say what the theorem means. Analysis, that is the proof is not difficult. Right? It's not difficult. It depends on how well you understand. But what would it mean in 2 dimensions? So let's try to understand. Let us imagine that we have a function which is from this rectangle. So this is a domain now. So not rectangle, sorry, square. So this is the square. Just like we had a closed interval, right? Now we are just taking this box.
No, I know. Like now, I'm also studying in metric spaces, so I'm like acquainted with this.
Right. So then you can relate these things, and you can tell me the metric space analogs. Okay. So fine. So this is the 0, and then we are taking the function f from here to r. Okay. So it is on r, but the function is on back to r. So we don't need to draw this. Now let's say f is continuous. So f is continuous. So since you would know what definition of continuity would mean in this case, from a box to R. Right? How you define continuity?
I haven't got to that part yet, continuity.
Right. Okay, but can you make a definition? We'll just take the definition,
Let me
not
try. Let me try. So basically, it should be somehow like an analog to R,
yes.
R to R. So in that we have got that limit of f of x as x tends to some point, x naught is f of x naught. That is the like
Yes, and you
condition
can
for
take this definition. Yeah.
yes. Here you've got 2 points x comma y.
But that's also a
X,
point. I mean, okay.
yeah, that's what. Yeah, 2 points in the sense. Yeah, but then we will give it a notation with capital X, that point x comma y maybe,
Right.
or
Okay.
something like
Mm-hmm.
so that if you take that limit,
A limit in what?
I think the if you see that the distance of this point from that number, so for example it will, if its limit is equal to L, so distance
No,
of
but limit
point,
to what? A limit of what? Some sequence? What sequence or what number? That is.
no, we are defining a function from closed interval 0 comma 1 cross 0 comma 1 to R, right?
Right.
And you are asking me that what is the condition for, or how can you define continuity for this function?
Right.
That is the question, right?
Yes.
So basically I'm saying that if so if x is a point in domain, it should go to some point L in its range, right?
Right.
So can I say this that the
Okay. So you try to formulate the definition, but we can just define it in all of the ways you're trying to say. Okay. The point here is that you can just say, okay, if any sequence converges to this, right? Any sequence of points which are themselves pair of points, and convergence of sequences you may have seen in R2, right?
right.
Right. Then the corresponding values here converge to L. You can take that definition, any number of definitions. The point is that we should intuitively understand what continuity means. Okay. Or you can also say that given any epsilon here, there is a delta ball here, so that all these points map in this epsilon.
Right.
That is also in a number of ways you can say. Okay. Point is not to know the continuity very well, but just to understand what roughly it means. But now let me come to but you think about it. Maybe now you can just go and read a little that continuity thing a little bit, or think first. The point that it is important that now, uh, uh, as you would expect, it is also true that you have uniform continuity. Here also continuity implies uniform continuity. Okay. But again, that is we will not prove it. Point now is that if I now have a finite cover of the rectangle, again, you see when you try to prove uniform continuity here, you will come down to the same thing, right? That every point you will have the delta ball, and then you'll have infinitely many balls. Then the Heine Borel, and so you'll assume that there are finitely many balls. But I'm coming to that delta, that one delta, which did the trick in our case, in the one dimension case. Now, if I have finitely many these things, what would you want? Again, you want a delta so that, I mean, the same thing basically. Right? You want a delta so that if 2 points are less than delta, meaning that if the distance between those 2 points in the rectangle is less than
Lie
that.
in some cover, some neighborhood of, I mean, they lie in some ball of some.
Yes.
Yeah.
Exactly, right. This interval will be replaced by neighbor. Okay, and here also the fact is true, but how do you prove it? Now you see it becomes more tricky to prove. Right. Now it seems more tricky to prove. What would you take? Minimum of the intersection of radius, this,
Because
that.
here, between two neighborhoods in R, there was like only one overlap, kind of.
Yes.
Here, there are multiple overlaps between two neighborhoods. I mean, for example, if you consider the region, like there can be three overlaps, right?
Yes.
I mean, three neighborhoods can overlap mutually.
Yes, that is, there are several kinds, and I've thought about this for very long, and I did not find a proof, a combinatorial proof. Like combinatorial in the sense that can you describe it in the sense of minimum of something, you you take the centers of the balls. I was trying for 2 circles and 3 circles, but it seems difficult, but it will work maybe, but we'll not go into that. Otherwise, we'll stray from the point that we are trying to make, because this comes later. First, we will try to see Heine Borel in an easy way. Okay, then, yeah. But this is called the Lebesgue number lemma, and this proved with 3-dimension, 4-dimension, but it becomes difficult to prove. Okay, but yeah. Anyways, let's not go more. Okay, so let us come back to what. So just, but the good thing is that for 1-dimension case, at least there is a very simple proof, and we sort of just highlight. We're able to use that without going into the hi-fi thing. Right. So the next thing should be to look at Heine Borel, right? This is the thing that we want. So let us just come to that. So maybe we can just call it what it is. But first we'll just prove it for an interval, and then maybe we can try to prove for a rectangle also today. And in fact,
so today basically we are going to like rigorously do Heine Borel, right?
Yeah, let us do this. Let us see. I mean, rigorously.
Corollary of this will just prove our uniform continuity, right?
Yes. Yeah. That will be fine, right? Yeah. Right. So, what is the statement? The statement is that if you have, okay, I mean, I already wrote it. Should have erased it. So this I, but you see, this I is not, this is not a finite union. It's a union, any collection, any collection. So, but yeah,
but shouldn't it be a countable collection?
No, that is the point. It need not even be a countable collection. It need not be a countable collection, but we will do it for a countable collection only. And the proof does not change if you do it for an uncountable collection, but it just adds the extra bit of symbolism, symbols, extra bit of extra symbols.
We can even do that, right? I mean, why not?
Yeah, no, that is fine. But the point is that yeah. So let's do that. So there is. There are, anyway, we'll come to that later. Yeah. So there are some things like any cover has so there are some places, like some kind of spaces, metric spaces, where you will see that any cover will have a countable subcover. And that is sort of proved separately. Okay. And then second thing is that any countable subcover has a finite cover. Okay. So like these two things are distinguished. In here, any cover will have a finite subcover. Okay, so it's proved directly. But then there are two breakings of this fact. And what happens in some places, one of it is true, but the other is not true. Okay, it becomes a lot of interesting But
how can this happen? That if any in an arbitrary metric space, if any cover has a countable subcover, and you are saying that the countable subcover has a finite cover, right?
no, I'm saying that these two are separate things. Like
Okay,
in
they are
some
separate.
one may happen, other.
I thought that we are going to prove that this has got finite subcover, countable subcover, and that countable has always got finite subcover.
Yes, so that is how one can also prove, because then that completes the result, as you said, right? But
Yeah.
then basically one stratifies it, right? There are two different layers one breaks it into, right? And then one can study each of those layers separately, and then there are some places in which one of them is true, other is not true, and that will allow you to say that. So that is why, or maybe not that is why, but just try to let's try to just see this first, okay? For the countable case, then we will go from the uncountable case to countable case, because I'm saying that going from uncountable case to countable case is not only true for closed intervals, but any subset of R. Okay, so that way you'll get more if you stratify the question. But all this is, I mean, doesn't have to be taken in one shot.
It's a bit abstract, and also
yeah. That's why let us just prove it for countable for now, and then we see.
But is this studied in the first year? This case for uncountable.
You can study. These are not hard things. Okay. Yeah. Once you study. People study. Those who have studied, they study. Those who don't want to study, they. It's not in the syllabus. So usually these things are investigated officially these things are investigated in what is called topology. Okay. So yeah. So anyway. So this is, and then we want to show that this implies that there is a finite subgroup. So maybe if you have thought about this, or you have, if you know the proof, you can say. I mean, so actually, you see, this is the wrong notation, right? I should not say AI BI only. I should say AI1, or no, sorry, AI. Oh, let me just. Yeah, it's better to write it like that, because you may not get it from the first, obviously, from the first I ones. So, right. So if you have any idea, you can say, and we can try to prove it from there. Right? Because this can be proved in any way. You start from anywhere and you can get a proof. That's not a problem.
Can you just explain the notation? I didn't understand.
Yes, yeah. So you understand the statement, right? That if there is any cover, then you can pick some finitely many of the among from them, which will also cover. And the notation part is just that this is just A1 B1 A2 B2 A3 B3 all are covering, and it's AI1 BI1 is
like a subsequence of
subsequence.
the
Yes, subsequence, exactly. Yeah.
Okay.
Right. Finite subsequence. And why not try to prove it using subsequences only then? Or any. So do you have any idea how we can start? So let
No,
us
so
just,
far I don't have any concrete idea.
so let us just maybe say that they don't cover. Any finite many of them don't cover. Right. Maybe you can use that. So just assume not true.
Hmm.
Then what can we do? So maybe then what we can do is we have this, and any finitely many of them don't cover this, right? So it means that now we're going to divide it into half with this bisection principle, binary search group. So this thing, then one of them will not be covered. One of them will not be covered by any finitely many of them. So 0, half.
Yeah. Mm-hmm.
So try to use this. Is not covered.
But then if 0, 1/2 is cannot be finite covered by finite number of covers, then 0, 1/4 or 1/4, 1/2 again, either of them cannot be covered by finitely many covers.
Right. Yeah. And we can assume it is one of them. That is not a problem. Yeah.
Hmm.
Okay.
Yeah,
So
and
then,
so on. We can continue, right? We can.
right.
So it decreases the size of the interval itself, right?
Yeah. It makes it half at each stage. Yes.
Yeah.
So we have like these intervals which are size is going to 0. The size is going to 0.
Right.
But maybe more better to say that they are decreasing. They are subsets of each
Even
other.
yeah, the subsets of each other, right? So like kind of nesting is going on.
Nested. Yes, it's exactly nesting. Right. Like not in a symmetric way, but it is nesting.
It is nested though.
Yeah.
But by Cantor intersection theorem, we have that, right? That even like in the intersection of all these things will have at least one element.
Yes. Intersection of all of them, there will be at least one element. So intersection of i's, and see, this is an infinite thing.
Right.
Infinite but countable. Okay, infinite but countable, because we have kind of taken steps, right? We have done n many steps, where n is natural numbers. So this is not empty, and in fact, it will have a unique point, right? This will have a unique point.
Have a unique point.
Yeah, so
Yeah, that can be proved by monotone convergence theorem.
right. That is exactly the Bolzano-Weierstrass theorem. Yes, that monotone convergence. Right.
Because here the AI is also getting increasing and the BIs are getting decreasing. And they must both must converge to their supremum and infimum respectively, and they'll be equal. We can have an argument that if
Yes.
the point is not unique, then it will become it will not follow their infimum and supremum property for AIs and BIs, something like that.
Right. So point is, you can see that it is exactly Bolzano-Weierstrass theorem. Right. There is nothing more in it. So this, and so from here also you can prove the Bolzano-Weierstrass theorem. You can try that for homework.
Right.
Okay. Yeah. Like from this property, Cantor intersection, prove Bolzano-Weierstrass. But
Right.
But yeah, now let's take this point x naught. Let us say it is here. And the situation is that we have sort of now a decreasing chain of intervals, and none of them are covered by finitely many, unfortunately. But everything is covered by something.
Yeah.
So then the x naught is covered by something. Let us say it is covered by something, some open interval.
Right.
But then, right, you can find eventually the nesting will come inside that open interval.
Yeah, it has to.
Because you can take the length and the minimum length and whatnot, right? So some, let's say some AK, BK. But then eventually the nesting will have to come inside because size will become. But then this nesting is getting covered by finitely many. It's getting covered by one. One.
Right.
That's a contradiction.
That's a contradiction, and yeah, this I didn't like think of using this bisection argument.
Yeah.
I haven't seen it in a long time.
Yeah. So it's, I mean, this is not my idea. This is a proof that I've read several times over several years. So,
Actually, what has happened that I like while studying the second layer of analysis, I am not that much like fluent in terms or in in like how I am with the one variable analysis.
yeah, but it is, you will get over time. That is the point. Over time you will get, because you did first did calculus, then you did analysis, right? Then you did the single variable analysis, something like that. The point here is that the multivariable analysis is even more difficult. Yeah, but maybe you can look at that a little bit. Maybe try to calculate limits of multivariable functions. Those things will give you intuition. Over time, it will have to happen.
Yeah, over time, obviously, because previously the epsilon delta used to like look a bit difficult, but now it's like getting used to, right? There is
Yes.
nothing new.
Yeah.
Very comfortable. But now this cover idea and this compact space and then these ideas are now like the new thing for me. So
yes,
I'm just struggling in
have to
that.
get comfortable with that. That's in maths, you will have to keep learning new things all the time. So every day, and you have to try to get comfortable with it. If you don't get comfortable with it, then you'll either stop liking it. That's what people say. I don't like this topic. I don't like that. Anyway, so this is one proof. Okay. Yeah. So we can try to prove this in the maybe yeah. Let's try to do it by a way which doesn't look like a contradiction. Yeah. So we can try to do that. Means after this meeting, I'll just end the meeting and launch it again. For the next
Yeah.
minutes.